I'll tell you what this picture means in a moment. That's just a little what we're going to do in the lecture. I'm going to talk a little bit about how you can test views with tests, then go into more detail into the formalities of the language of hypothesis tests, the terminology that surrounds them, so applying ideas that you've already met, making sure that you have the terminology correct. Then we'll look at some different types of t-tests and examples. I think there's about 3 different types of t-tests. Then a different one which is called the chi-squared test of association. Then confidence intervals, which you might have met last year, and some conclusions. So first we'll look at how we can test views. And this was something that was in the news last year, was World Food Programme aid to Somalia, which was being diverted for sale in local markets. And they couldn't work out, there was controversy over whether this is really going on, because it always happens to some extent. Always some grain gets sold. You can see here that that's World Food Programme grain there. And they were trying to work out, is this a really big problem this year? Because some people had claimed that half the aid to Somalia had been diverted to private sale. So was it as big as that, or was it just a small amount? So we could test what are the real proportions that are going into the private market. These people didn't want to be interviewed for obvious reasons. We'll also be talking a little bit about how you can, during the workshops, about how you can ask people questions when it's about things they don't really want to talk about, like the question we had last week about illegal drugs. You can ask people's views about, should aid go into food aid if it gets stolen? Is aid being stolen on a wide scale? You can ask people's views about that in this country as well. The golden taps I told you about last year. Is it time that Britain turned off the golden taps, as some Conservative lord put it, of aid? This links to your coursework. In your coursework there's 2 parts. First part is looking at evidence on a topic in literature. The second part, you have to analyse raw data. The 2 ways that people have done that in the past is either downloading it from secondary sources and analysing it, or collecting your own data, either direct measurements on campus or interviews or a small SurveyMonkey thing. One type of thing you can ask people about in this country is views. Because obviously you're limited, you can't really travel to a developing country unless you're very ambitious, just for this essay. So if you want to talk about a topic that affects the developing world like these I showed you there, you can ask people in this country about their views. Some ideas that people have tried before is an observational study, so a big survey. So gather data on views, what's your views on aid, and gather other data on sex, education, age, see if there's any link between people's sex, their education, their age, their background, and their views on aid. Or you could try and do an active intervention and experiments, so give people a simple questionnaire on their views on aid, but randomly in one group give them some extra information, either pro or against different groups, and see does that have an effect on what they say about aid. If they've read something by Dambisa Moyo, some quote saying that it's all being pinched and stolen, it's hopeless, will they give more? Will they be more favourable towards aid? So you can do, if you want to do an RCT, an intervention can be just giving people some extra information. Hi. So let's just say, for example, we had a question we wanted to ask. The UK is trying, along with, I think, health, education, it's keeping aid budget fixed. And we're working towards this 0.7% of GDP. Let's say you could ask people a simple question like this. Should aid be protected from the cuts we're having? And suppose you might think that dev students would be less likely to say no, that you think that dev students would be more likely to want aid to be protected. Now you gather some data from 84 students, maybe SurveyMonkey. What would you expect to find? If you really think that dev students are probably more pro, more yes aid, well, here's some possibilities that you could find. You could see one of those 2 things. You could find that in your sample that dev students, these are 2 possibilities in the whole population, not sample, scratch them. The truth could be that either dev students are not more likely to say yes, or they are more likely to say yes. Of course, we can't just look at that. We can't directly observe each possibility. You can't just see all dev students, possibly all the past ones and future dev students. Are they more likely to say yes or no? We can't observe that directly. So all we have is your little sample of 84. So the 2 things you can actually see are, in the sample, the percentage of students is saying yes is a little bit higher among dev students, or about the same, or even less. So I'm not sure you can see these very much. So possibilities here are these ones here, the population. I tried to draw some possibilities. The big circle is the whole population, all the possible dev students. And it could be that they're about the same views there, or dev could be slightly more negative towards aid, or dev could be much more positive, like here. But you can't observe that. All you can observe in each case is a little sample. And these are the possibilities in your sample. You could find that dev students are a little bit more negative about aid, a little bit more positive, about the same, or much more positive. And based on what you see in your little sample, from your sample you've got to tell what's happening in the whole population. That's the puzzle. So you might see that or that. Now how are you going to conclude from this which one of these populations we've got? Well, this is the obvious link. If you find that if in the whole population dev students are not more likely to say yes, you're more likely to see that. So if that's the real truth that you can't see, this one could happen. But if that's the real truth, you can see that dev students are more likely to say yes, that's what we think, then you're more likely to see this. Yeah. Okay? So that's the straightforward one. If dev students are no more pro-aid than anyone else, you're going to get that. Randomly, you could get a dev student saying a bit more, but really that's just random. So it can be quite close. But if dev students are more likely to say yes, you're going to get the dev students really much more in your sample. So in this last scenario here. So dev students are more likely in the population. You're going to get this nice big difference here. The problem is, of course, that you also could see this. You could find that in the whole population, dev students are not more likely to say yes. But when you do your sample, you actually get, because of the ones you happen to pick, they're much more likely to say yes, or the other way around. Dev students are actually more pro-aid, but when you get a sample, you get some sort of cynical ones, and they aren't. They may be even less likely to say yes in your sample. So your sample could completely reverse, as I tried to show there. It might be that dev students are slightly ahead, as one of these shows, but in actual fact we get the non-dev students ahead when we do the survey. So the question is, you can't see any of that. You can just see one of these two things, and you've got to try and say which of these is happening. Well, you can put it out in what we call a tree diagram like this. From the start, we either have this or this. We want to know which one we're in. We can't observe that. And the bad news is, we're doing statistics. You can never say for certain which of these is true. Forget that. So you can't do that. But, in other words, if you see this, the problem is that these two things occur twice. If you see that in your sample, the sample of students among dev is less than or about the same, or perhaps a bit higher in the dev students, that's identical whether you see it here or here. Whether it's come from dev students not being likely to say yes, or whether it's come from them being likely to say yes. And just because you see that thing I picked out in white, you don't know whether you're here or here. And that's the problem. What can you conclude? What you can do, you can say something about the probabilities that you're here or here. That's all you can really do from a test. If you see one of those or one of those, you can say which of these that tells you which is more likely, perhaps. Gives you some information about which is more likely. Based on these probabilities here, you need to know these probabilities. If that's true, what's the chance of that happening? If that's true, what's the chance of that happening? And so on. Now, this is an important idea to understand. We normally expect the thicker arrows here to be more probable. So perhaps stop me here if you're not sure why the thicker arrows. Why are these thicker arrows? We expect them to be more probable. Yeah. So if in the whole population dev students are more pro-aid, are not more pro-aid, we're up here. If in the whole student, there's no real difference. Dev students and non-dev students are pretty much the same views. If that's true, then you're more likely in your sample to get that kind of same result. But it's possible, so a thin arrow, it's possible that you could happen to choose a sample where the dev students are considerably in front. The opposite thing is the case. If it's true that dev students are in general more keen on aid, then you're more likely to find that in your sample. But slightly less likely, you could find that they're only slightly more keen or even less keen in your sample. So can you see, for a start, that all these four possibilities are possible, but that the ones with the bigger arrows are more probable? Because that's the key to all the hypothesis tests. Then all the mechanics of the hypothesis test is in a certain situation, how do you actually figure out the real size of these probabilities? That's the difference between different kinds of tests. What maths do you have to do to figure out the size of those arrows, and then you can figure out whether you're more likely to be here or more likely to be here. That's what we'll go through. If, for example, we see in our sample of students that the dev students are much more enthusiastic about aid and much more likely to say yes than the non-dev students, then what can we conclude from that? Can we tell that we are up here or down here? We can't be completely sure, but because it's much more likely, if the dev students are more likely to say yes, we're much more likely to come down this fat arrow here than we are if dev students are not more likely to say yes, even though it's possible. Although we can't tell for sure whether we're up here, the top one of these black ones in black text or at the bottom, it does make it more likely that we're down here. So if we observe that dev students in our sample tend to say are more enthusiastic about aid, that suggests they're more likely in the population to be enthusiastic about aid. Conversely, if we observe the opposite, that there's not a lot of difference, or dev students are a little less or a little bit more likely to be in favour of aid in our sample, again, we can't be sure whether we're in the top of these two situations here or in the bottom one, because they look the same. We're seeing students saying around the same, slightly more among dev, perhaps slightly less, saying yes. We can't be sure which of these two hypotheses to accept, but because it's more likely to be going up this thick blue arrow here, it does seem to suggest that it's more likely that the dev students are not more likely to say yes. But we can't be sure about that, but it suggests that the probability is higher. So, summary is then, are dev students actually more likely to say yes? You can't tell for certain if it's true. That's the bad news. Can't tell for certain. All you can do is say something about the probability that it's true. You still can't find the actual probability that they can say yes or no. All you can find out is, how does this observation change what we already knew about this probability? All that tests tell you is, how can you change what you already know? You have a starting point. So now let's put this kind of vague language into the language you'll see in textbooks and articles. So for a start, what I have called so far an idea about the world, we usually call a hypothesis. So a theory about the way the world is a hypothesis. It's a possibility. For example, dev students are not more likely to say yes. It's what I called an assumed theory before in the last lecture. But we normally state it more precisely. So instead of a vague thing, we'd say precisely like this. So a hypothesis is the proportion of people who would answer yes is not higher among dev students than among non-dev students at UEA. And a simple test helps you decide between two. As you'll see, there's other tests that help you decide between many hypotheses, but the simple ones just have two hypotheses. And these have got to be exhaustive. Exhaustive means if one of them is wrong, the other one's got to be true. So those two hypotheses, they're the only possibilities you think there are. So if you have someone that comes from Britain, your two hypotheses can't be one hypothesis they come from England, the other hypothesis they come from Scotland. Because you could rule both those out and they come from Wales or Northern Ireland, so it doesn't quite work. They've got to be completely exhaustive. You've got to have one hypothesis at least which lets you work out exact probabilities. Otherwise you're stuck. And that one's usually called the null hypothesis, and the other one's called the alternative. Common shorthand is this: H0 is null, H1 is alternative. So we'll stick to that. Some books you have H0 is null and HA is alternative. Reject. If you observe something which has a very low probability of happening, if the hypothesis is true, then you reject it. So if we assume this is true, if that's true, then what we've seen is very unlikely. We reject the idea. Logically, that means that because we have started with two hypotheses which are exhaustive, if we reject one, logically you have to accept the other one. That's why you have two that are exhaustive. You can't show support for one of these logically unless you reject one of them. All you can do with hypotheses, if you find evidence that agrees with one, then that doesn't show it's definitely true. That just supports it. The famous example is with swans. If I have a theory about the world, my hypothesis that all swans are white, if I find 50 white swans, that's great, that helps, that supports it. It doesn't prove it, it just supports it. 100 white swans, 1,000 white swans, it supports it. If I find one black swan, that theory is now dead. It's much more powerful to disprove something than it is just to add stuff that supports it. So quite often, we set up the null hypothesis, what we want to reject, because rejection is a much more powerful thing. Normally, the hypothesis we expect to support is the alternative, and the one we hope to reject is the null. Okay, now hypothesis test. Because you're dealing with probabilities, there's no certainties. Very likely you're going to make some errors. You can't rule out errors. Logically, there's two different sorts, and you'll hear this referred to a lot, and maybe you have already met it. The two types, logically, you can distinguish is the type 1 and type 2. For example, in the one I gave you above, if that's a null hypothesis, then which outcomes lead us to reject this? Well, it's if we see that. So if this is what we start believing, that dev students are no more likely than non-dev to say yes. If we see this, we're not going to reject it. If we see this, we will reject it. But we don't know whether we're here or here. So if we're actually here, we've made a mistake because it's true. If we're here, we're right. And that would be a type 1 error if we make that error. Now, problem is the test never tells us the value. The test never tells us that value. That's the probability that was true before we even did the test. So before we did this test, what did dev students think about aid? We can't find that value. And it also doesn't tell us. It doesn't tell us the value before the test, or alpha is just giving us this, the probability of reject, if it's true. That's the only thing we really know. So alpha, written in symbols, is like this. Alpha is the probability of rejecting it if it's true. So the test value you get from your computer when you do your test is the probability of rejecting that if it's actually true. And beta is the probability of not rejecting it if it's false. But that's if it's true or if it's false. We don't know whether it's true or false, unfortunately. However, if you do have a belief, so if you've got either a belief or lots of prior evidence, before you've done your test, if you've got some beliefs about this based on prior evidence, what's the probability it's true or afterwards? What the test will let you do is work out, after you've done it, what's the probability now that this is true or false? So in order to work out, what you really want to know is, after you've done your test, what's the chance that this is true and what's the chance this is true? In order to work out that, you've got to know this probability and this probability here, and also what it was to begin with. So what the previous evidence said. So if you've got a belief about the prior probability before you did the test, and you know alpha and you know beta, then you can work out this, which is what you really want to know, which is the opposite of this one. You don't want to know you know the probability of rejecting if it's true. What's the probability that it's true given you've got to reject results? So given that you've seen the dev students ahead in your sample, what's the chance that means they're ahead in the population? That's what you really want to know. But it's very rarely the case you can put a number on that. Okay, enough grand theories. Let's just go through lots of examples. So types of tests and examples. Okay. So the language and logic of that applies to all tests. So the difference is the kind of hypotheses you can test, the assumptions that you need to make, and then the maths, how you work out those probabilities, alpha and beta if possible. Some tests use this t-distribution, which is very similar to the normal, just slightly wider. Started looking at those in workshops we'll carry on. Let's look at some of those. So first, this is the one you have seen. This is called one sample t-test. And it's used to test the mean of population. So that's what you need for that. You need to have some idea about what is the mean of the population. And you need a single sample, which is why it's called a single sample or one sample t-test. The null hypothesis is that the mean is that thing you think it is. The alternative can be two-sided or one-sided. Depends what you want to test it. If someone gives you a figure and you just think that you're not sure that figure's true, you think, is it accurate? Then you would reject that figure. If you find a value much higher or much lower, you reject it. That's a two-sided one. So in that case, the alternative would be the population mean is not that. But if you, for some reason, think that you can rule out being less, you think the population's gone up, the mean's gone up, your alternative would be it's greater than that. Similarly, if you think it's gone down, your alternative would be that it's less than that. So these are two one-sided. So here's an example, a concrete example. Small farms in an area of South Africa, maize yields known to be 496 kilograms per hectare. Which seems a bit low, but they are. That's maize, okay. Yeah. 496 kilograms per hectare. A new variety of seeds introduced. 3 years later, random sample of farms. Have small farm yields increased in that area? And here's the null and alternative hypothesis. The null is that the mean is this. The alternative is that it's greater if it's a one-sided. Because you want to see if it's increased. So if you find a decrease, you wouldn't reject the null. You're only going to reject it if you find an increase. Now you look at the data and find what the probabilities are. We'll go through, we can look at, if you have any questions about the mechanics of these, this is what we're doing in the workshops, how you get these sums, but what you need to know is the sample standard deviation, how spread out is your data. Work that out. Because you're getting a sample, you divide by the square root of the sample size. So divide by the square root of 20. So this is the standard deviation of sample means if you took samples with size 20. Then work out a similar way to the z-score, except because you're using an estimated standard deviation, it's actually a t-score. So the difference between what you found a mean of that. That's the mean you found. The difference between there and there. How many standard deviations is that? Well, it's that many. How many standard errors, sorry? 2.887. So the t-score, instead of z-score, is 2.887. So it's 2.887 standard deviations from the mean. And you can look up in tables on the computer what's the chance of getting a value like that in the t-distribution. So in Excel, that's the formula you put in. Type that in. results. So, if H0 is true, chances of choosing a random sample of 20 with a mean as far away as that from 496 is 0.004723. So if it's true that maze yields in this area are still 496, which, if that's true, then the chance of selecting 20 at random and getting 555, which is what we got, the chance of getting that is that less than 5 thousandths of a percent. So less than 1 in 5,000, sorry. So it's less than 0.5%. So I can reject, because it's less than 0.001, I can reject with 99% confidence in favour of H1. So even though we're short on time, I shall show you this again. I've got some equipment we can use in the class. Does anyone have any problems with radiation? Or flashing lights? Or anyone worried about Wi-Fi, phone signals, that sort of thing? Imagine here we have the idea we want to test. Imagine here is 496. That's the idea we want to test. The observation is 555. What we're trying to get is the probability of that happening. Well, what we do is we connect up over here. Oh no, the wires got tangled. Shit. Here's the 496 over there. Yeah. The 496 is here. That's what we think. Then we connect this to the observation, and this works for any hypothesis. This tells us how likely is it, given this 496, what's the chance of seeing 455? And it's come up to here, so it's come up to less than 1%. Yeah. So the thing we're measuring, and how we measure the surprisingness is this. This is the t-value. T-value gets bigger and bigger, the probability gets smaller and smaller. So once we get into this kind of area, this means it's hyper surprising. If this thing's true, the chance of seeing this is incredibly low. So this means reject. So big surprise, this theory over here cannot be true. So we reject it. We'll come back to that complicated stuff in a moment. So in QED, that's the bit we'd like you to be able to do by hand. So in the QED test, just that one sample t-test, these because with an RCT you have two groups, we have the means. They were given training in microfinance, and one group were given training using accountancy, basic accountancy, like double entry bookkeeping, all these accountancy laws. Other groups were given simple rules of thumb about look at costs as well as benefits, and when someone pays you money, always bear in mind that inflation, simple things like that, instead of going through the whole bookkeeping rules. And they tested to find which of these two groups does better, which two groups has a better increase. And the null and alternative is this. The null was, in the population, the mean income change is the same. Alternative is that it's not the same, so there's a difference, two-sided. That's what the data would look like in Excel or SPSS, the kind of training they got, and then the change in weekly income. So in SPSS, you put it in there, compare the means of these with the means of those, press OK, and you get this coming out. Two significant values. So, yeah, maybe you'll have time to discuss more with Sandra. In SPSS, it gives two different independent t-tests. These are the significant values. Often they're very, very close. It's down to the question of whether or not the variance in those two populations you can assume is the same. Regardless of which one we which, you get a similar result, 0.35. It's a two-sided test, so we don't have to divide them by 2, so our figure is around about 0.3. So if this is the theory you have over here, so the theory in this case is that this training makes no difference. So if the training makes no difference, that's my null hypothesis. Means are the same, mean increase in income is the same. The observation is that here's the difference in means here, 627.623. That's the difference in means we actually saw. What's the chance of getting a difference that big, given the observation? About 30%, 35%. So that's the probability of seeing this. If the null is true, that it doesn't really make a difference, there's that much chance of it coming up. So in that case, it's not unlikely enough to reject. So we have to live with it. Perhaps the training didn't make any difference. So we can't reject this idea that in the population, nothing's happening in that case. So the way you interpret it, exactly the same as t-test. So there's null and alternative hypothesis. We found a p-value of well over 0.1, so we can't reject it at all. Can't reject H0 at any significance level. I think that should be got rid of that. So the evidence provides no support for a claim that the two methods have a different effect. Test of correlation. And this again is a kind of t-test. You got what you need for a correlation test is a random sample with scale variables x and y. And the null hypothesis is that, okay, you might have a scatter with a population, you might have a sample with a scatter, it looks like there's a correlation, but the null hypothesis is that in the whole population, there's no correlation there. The alternative hypothesis is that they are correlated, and it can be one or two-sided. It can be that it's positive, negative, or just correlated in some way. Here's the bit we're not going to test you on. You can show that if you take the correlation coefficient and do that with it. So that's the correlation coefficient, that's the number in your sample. If you calculate that, that gives you a t statistic. You can show that, but we're not going to test you on it. So, example, fertilizer and maize. Does increased fertilizer use on small farms raise yields? Bear in mind that idea. Here's the null and alternative hypothesis. In the population, fertilizer application rates and maize yields are not correlated. The alternative is that they are positively correlated, so it's a one-sided alternative. Bear in mind, though, that even if you get some evidence for this, it doesn't directly show that because this is about causality. So it supports that, but it doesn't show it's true because it's causality. There could be another link. But at least it shows that they are connected in the population. So it might have nice external validity, showing that applies on a wide scale, that pattern, but no internal validity. We haven't shown causality. We're going for external validity here. So here's what you got in your sample. Looks pretty good. Positive coefficient. So that's, of course, you wouldn't expect a fraction of people. You might say you might expect 30 and 28, but that's nearer. So basically, you're sharing out the men and women according to these proportions. You could do the same calculation this way, sharing out the rice fields in this proportion. It comes to the same thing. Because what you end up doing is you multiply that by that and divide by that, whichever way around you do it. So that gives you all these, do the same thing for that and the same thing for that. So you end up with, that's what you'd expect if there's no connection between them. So these are the things you end up with. That's what we've observed. That's what we think there would be if there was no association at all. What you need to do is work out a way of saying how far is what you've observed from what you expect. And this, again, this gets to the bit we're not going to test you on. There's a way of working out how far that is from that, which is we look at the differences. So go through each one of these, work out what's the difference between here and here, and you get these. So it's quite big differences there, and they're quite close to what you expect with millets. And this is the bit we're not going to test you on. If you get all these results, all the differences, the squared difference divided by the expected value, add them up, like that. So you square each difference and divide by the expected value. That gives you something which follows what's called a chi-squared distribution, which is just another random variable distribution. Its actual fact is, if you take a normal distribution and square it, you get the simplest chi-squared distribution. So, I think that works. And the most radical thing about this, that's the normal. If you square it, every time you get something here, you get a positive number because it's going to be squared, so there's no negatives. So it all comes to this side. So if you get positive or negative, they come here. So these all get, it kind of looks something like this. And that's a chi-squared distribution. And then you can work out what's the probability of being in any given percentage. But you don't need to know the details of that. So chi-squareds are normal distributions squared and added up if there's, like here, there's several of them. So that's the calculation you do. But all you need to do is shove it in SPSS. So in SPSS, you've got something like this. If you're in a situation in SPSS where you've got two categories here, is there any association between these two? Here's where you can do your chi-square test. The chi-square test comes out like this. It does the table with what you saw and what you expect and the differences. And it tells you what's the chance of being, if there's no connection, what's the chance of getting differences this big, and it turns out here to be 10%. So if there's no connection between the sex of the woman, and that's the idea, no connection between sex and the crop choice, the chance of seeing the difference we saw comes out at just over 10%. So you can't, it throws a bit of doubt on it, but you can't quite reject it at 10%. But if you're writing an essay or a paper, you'd say we can't quite reject it at 10%, but it's close. So there's no strong evidence here that men and women tend to grow different crops. Right. Confidence intervals, I think I have to go through the detail in the workshop, but confidence intervals are a more positive thing. Instead of starting with a particular hypothesis and accepting and rejecting, they give the reader something, almost the reader can do their own hypothesis tests. Okay. Suppose that we're given this information. How long did I press for it? Suppose we're given that information. We're told that mean income in a sample of households is that in rural areas and that 377 in urban areas. Can you say whether in the whole population there's a difference in mean incomes? Or can you say whether mean rural income is below a certain figure? Well, you have to do t-tests for that. But suppose you're told this. Suppose you're given what's called a confidence interval. If you're told that 95% confidence interval is between that and that for rural areas and that for urban areas, then the reader can tell both those things themselves just by reading this. You can tell that it's likely there's a difference in means between rural and urban areas, because you know that rural areas the mean for rural areas is somewhere in here, and the mean for urban areas is somewhere in here, and they don't quite overlap. because they don't overlap, the person that's reading can say, well, okay, I'm not sure exactly what it is in rural areas, I'm not sure exactly what it is in urban areas, but because they don't overlap, we're pretty confident they're different. And also because it doesn't give strong support to the idea that in rural areas it's less than 350, because 350 is in this range, you can't be at all confident that the rural area is above or below 350, because all we know is the mean is 347. Yeah? But it goes right up, the confidence interval goes right up to 366. So the person that's reading can tell a lot more about where the means are likely to be than they can if you only give the mean in your sample. So related to t-test, suppose we had a sample like this, 9 heads of household. You can do a t-test to find out, is the population likely to be more or less than 43? So that's what happened. We've got it on the screen here. If you do a one-sided t-test, or two-sided test, is it likely to be 43? There's a probability you can't reject it. So you can't reject the idea that the population mean age is equal to 43. So much for the t-test. A confidence interval is like doing every kind of t-test at once and seeing which null hypothesis you would accept or reject. By trial and error, you could do this. Instead of testing 43, we test 40. And it gets a bit less likely there, because what we observed was, in our sample, the observation was, no, I can't tell. It's a bit annoying. It's 45. 45 is the mean we got. So 43, we can't reject it. If we go down to 40, it's quite unlikely we get as big as 45. If we go to 39, you can reject it. So somewhere between 40 and 39, if that was the mean, we'd reject it. And similarly at the other side, how big would it have to be? So it'd be too far below. That's the exact value there by trial and error. If you go to the other end, the top end, if the population mean was 49, 45 would be so surprisingly low, not quite surprising enough. If you went to there, it would be exactly 0.05. So if the true population mean is anywhere between 49 and a bit, 50.05454, and if we do a t-test using any value between here and here, we won't reject the idea that we won't reject that possibility. So the real population mean could be anywhere between there and there. We wouldn't reject it. If it goes outside that range there, then we would reject it. So this is what we call the 95% confidence interval. We'll do more on that in the workshop. Again, in SPSS, all you do is put the data in. It gives you straight away the confidence interval. So conclusions. The logic and terminology of all hypothesis tests are the same or common. You have null, alternate hypothesis, reject, non-reject, type 1, type 2 errors. There's different kinds of tests for different kinds of things. There's testing means and differences between means. One sample t-test, two sample t-tests, correlations, chi-squared tests. And confidence intervals almost let the reader do their own tests. So I'd really recommend that whenever you gather some numerical data, instead of just saying the mean of my data is this, give a confidence interval, and then the reader can tell themselves, how confident can I be about where the real mean is. Okay, so, sorry that was a rush, but there's much more time to unpack this in the workshops tomorrow. But does anybody have any questions?